Okay, so the next project, which we just started about maybe, I don't know, a month ago, is very similar title. I just noticed after the schedule was posted. Usually I'm careful with these, but it's a different work because it's a different network. It's the Ripple's transaction network this time. And here, maybe it's related to the keynote speech. We are looking at decentralized credit networks, which are emerging as innovative solutions. And Ripple has one, which is, I think, one of the most widely adopted ones. It's pretty similar to Swift, but with the promise of being faster and with lower cost. And here again, we are looking at, from the perspective of resilience, what happens to the overall topology of the network if some nodes are removed or attacked. And here maybe especially gateways, those really important nodes being faulty is one of the bad scenarios, and we like to understand the consequences of them. But there are other metrics that we didn't really look at in the peer-to-peer scenario. What is the community structure? And there is maybe other metrics that go beyond the topology, like what is the overall throughput? Or when an adversarial attack happens, which amount of maybe credits or balances are frozen and cannot be reached. So we will be looking at those types of things. So this work is inspired by mainly a couple of, or the prior work could be listed here as the two papers here. The one by Moreno and Sanchez, or Moreno Sanchez et al., has really done a good chunk of what we want to do, but they have done it in 2018. So the data for now is not really fresh. So we like to repeat the analysis with the freshest data from Ripple's transaction network. Another paper here looked at Ripple's transaction network very recently, but they didn't do any resilience analysis. It purely focused on very basic graph theoretical metrics, degree distribution, clustering coefficient, and so on and so forth. So with that, let's look at what the Ripple's network, transaction network looks like today. First of all, we have to distinguish between two different transactions. One of them is direct XRP exchanges, which doesn't really require a network. It is handled at the application layer. If I want to send you an XRP, a certain amount of XRP, we don't need to have a path connecting us. But the second type of transaction supported by this network does require a network and does require a path of edges between the sender and the receiver, and this is used solely for non-XRP transactions. So it's either fiat money or other cryptocurrencies. And typically, although it is technically a decentralized credit network, what happens from my understanding is that there are these big nodes, so to speak. They are gateways. Everybody creates a wallet with them, and if they want to, transact funds among each other, it usually goes through GitHub, Bitstamp, and similar gateways. So the data sources here will Ripple's own API allows crawling, as well as the second paper I listed in the previous slide has the data from early 2022. So again, this is early project, so I won't be presenting results, but I will be presenting our ideas. So in this particular network, node failures could come from a gateway maybe having a technical issue and not able to support the network, or it could be from an adversarial attack, maybe adversarial wallet compromise. And the consequence of an attack, as I mentioned, is a little more than just the topology of the network changing. We also have the credit links, the links that are incident on a faulty node are effectively frozen, which means that some balance will not potentially ever be useful again. So the 2018 paper mentions that millions of dollars worth of coins are actually frozen and never potentially be accessed ever again. Once again, we will consider random and targeted attacks, and with the targeted attack strategies, highest degree, highest bit winners can still be used. But here there is also a different consideration. A node having a lot of connections may not mean it is the most important one. We will look at the number of transactions that go through the node, or the total transaction volume that goes through a node as part of the attack strategy. We will also potentially, I think, look at optimal attack problem, not to give ideas, I guess, to bad guys, but to understand the worst case resilience of our own network and potentially find better mitigation strategies. An important question I'm interested in is to figure out if there are still nodes that are deemed to be too big to fail. The 2018 study said that there were actually a few nodes that if they are gone, the network is not very useful at all. And that's not something we would want from a decentralized system. So ideally, it shouldn't be that just a few nodes are really holding the network together. So with that mindset, the metrics to be studied again will be the largest connected component size in the remaining network when some fraction of nodes fail. But again, we will look at not just the topological feature, but the total transaction throughput that could be supported in the remaining network and how much credit is frozen as a result of the attack as metrics to quantify the resilience. And additional metrics that go perhaps beyond resilience could be considered the number and size of the communities, like if the network has a bunch of different disconnected components, what is their size, and the distribution, and in result of an attack, how that changes. And also, most critical nodes will be looked at as well. Once again, I'm thinking that ideas from the chaos graph could be used to improve the resilience here. I fully realize that we cannot design this network. It's supposed to be decentralized. Individuals will create wallets and will be connected to whomever they want. But perhaps we can encourage or impose some additional links. I don't know the exact mechanism, but perhaps through these gateway links to make this network more resilient. So that's going to be one of our focus as well. Once the initial resilience analysis is completed, we will at least hypothetically see what will happen if the network was appended, again using ideas from the random chaos graph. With that, I think I've completed my talk. Thank you so much for the support, and happy to take questions.
Thanks for the interesting talks. What I see in Ethereum or other chains is that the network is more centralized, meaning that there are a node with hundreds of connections. To reduce latency and extract more MAV opportunities. So I'm wondering if you think your approach still hold for larger chains like Ethereum. That's my question.
Yeah, it's a great question. I think if it is almost fully decentralized, I think it wouldn't be very meaningful. Like what we are doing, it's going to be essentially failing. Any set of nodes would not really harm the network except that central node, and it's probably not feasible for an adversary to take over the central node. But again, this work is more for maybe decentralized, fully decentralized cases. So yeah, it wouldn't apply to Ethereum, I think.
Hi, I wanted to ask if in Ripple the peer-to-peer network is unstructured. Is it constructed randomly, or is it constructed in some structured way? Because I guess the Ripple protocol is based on some sort of social trust.
Right. So my understanding is it's really the nodes who are like the individuals or entities are creating these links. As far as I know, there is no structure imposed by Ripple itself for the path-based settlement transactions. That's my understanding.
No, I meant for the peer-to-peer network, actually.
Oh, for the other work. Okay, so yeah, that's a good question. Let me see if I can find that. Yeah, maybe I should have had one set of slides for both talks. Yeah, for that one, it's a good question. So let me perhaps, touch base with you offline and try to answer it more definitively. So this one may have more structure. Like, I don't know on top of my head, but yeah, I'll look into it and find you offline.
Okay.
Let's thank Osman. Oh, okay. A quick question.
Maybe Julia knows if
34 seconds,
the
Julia.
answer to the previous question.
I'll be very quick. Is there something specific about the transaction graph in Ripple that would prevent you from using the same techniques to analyze like the Lightning Network? Which, like the Lightning Network also has credit and topology
I don't
that you
think
can
there is
control.
anything specific to it that will prevent it. So what kind of specific thing you could think of that would make the analysis different?
I can't think of anything, so I was kind of
I
wondering
see.
why you focused on Ripple, if you're looking also at other...
Well, Good question. Why we focused on Ripple? Part of it is I think that was part of the call that encouraged, I think. Right. And another thing is it has a native crawler with Lightning Network. I mean, you know better. Is it possible to extract the exact topology with Lightning? Okay. So we will include that in our future research then. Thank you.